Okay, good morning. Today we're going to talk about the polynomial time hierarchy. It's kind of a classic topic. Actually, if you took like the undergrad class 455 last semester, we already spent 2 topics on it, but I'm not going to assume you know it necessarily, or at least I want to review it because it's a classic, and it doesn't hurt to see it a couple times. So this is a story of some complexity classes that are not considered feasible. They're above P. They're less than P space, so they're not too crazy. But as we'll see in complexity theory, it's worth it to study these classes. They help us study feasible complexity as well as the relationship between P and NP quite a bit. So they'll play a major role in that course. Okay. There's also several different ways to define the polynomial time hierarchy. We'll see at least a couple today, or maybe even a third, depending on how much time we get. So one way to motivate the polynomial time hierarchy is to ask the following question. Well, we don't believe it's true, but suppose, it's worth thinking about these things at least some fraction of your time. What happens if the unthinkable happens and NP equals P? And the question is, then what else is in P? Well, you might say, what do you mean, what else is in P? We got everything in NP. What more do you want? But it's quite easy to see that actually languages that we didn't think were in NP are also in P. So in some sense, as we're going to see today, the answer is all the languages in the polynomial time hierarchy will also be in P. Okay, so I'm going to define this polynomial time hierarchy, which is a collection of complexity classes today. So as an example, of course, we know that if NP is equal to P, then SAD is in P. In fact, that's equivalent. But this also implies that the unsat problem is in P. Okay, the unsat problem is to tell, given a Boolean formula, if it's not satisfiable. Okay, well, if SAT's in P, you just run your polynomial time algorithm on the formula, find out if it's satisfiable or not, and then you can answer this question. And notice that this problem is not known to be in P. In fact, it's quite strongly believed to, not known to be in NP. Okay, in fact, it's quite believed that it's not in NP. But nevertheless, it becomes in P in the case that NP equals P. Okay. Another way to see it is the following. If NP equals P, if you want to be a little bit formalistic about it, you can take the co of both sides. So we get the co-NP equals co-P. Well, that's just P, because P is closed under complement. So if NP equals P, then co-NP also equals P. And for example, unsat is co-NP complete. Well, it's in co-NP, so it's certainly in P. In fact, it's co-NP complete. Okay. So, in other words, just to quickly illustrate this phenomenon, not only all the languages in NP become in P, but also some languages that previously we didn't even think were in NP also go into P. In fact, there's more. So let me give you another example, which is a good motivating example, I think, for studying the polynomial time hierarchy. So I'm going to define another language here called minimum circuit, which I'll abbreviate thus, minimum circuit. Roughly speaking, it's the problem of I give you like a Boolean circuit. It computes some Boolean function, and you want to know, yes or no, is there like a better circuit computing the same function, where better means fewer gates? Well, I'll define it in this way. Min circuit is all the language of all the encodings of Boolean circuit C, such that C is the smallest circuit, smallest in terms of size, meaning number of gates, computing the same thing as C. Which I'll write like this, computing the truth table of C. Okay, so in this formulation, min circuit is a language of all circuits C that are kind of like optimal for doing the job that they're doing. Okay, so let's think about this language for a moment and what complexity classes it might be in. So first thing we might ask ourselves, okay, it looks pretty hard. It doesn't look like it's going to be in polynomial time to start. So let's go up a little bit higher. So ask, is it in NP? Okay, so intuitively you think to yourself, well, could there be any polynomial size certificate that would convince me, a polynomial time person, that this circuit is optimal? That's not so clear. In fact, it's believed that this language is not in NP. What about in co-NP? This one actually looks a little better at first. So I mean, what does it mean to be in co-NP? Roughly speaking, it means that whenever a string is not in the language, there's a certificate that can convince you. So if a string is not in the min circuit language, that means it's a circuit where there's a better, smaller circuit that does the same job. So at first you might think, oh, yeah, there is going to be a certificate that convinces me of that, namely the description of the smaller circuit that does the same job. But that's still a problem, because how are you going to check? If someone provides you with a smaller circuit and says, hey, this has the same truth table as C, how are you going to check that for yourself as a polynomial time verifier? It's not clear. So it doesn't seem that it's in NP, and it doesn't seem that it's in co-NP. It's believed to not be in either of them. But what we're going to see is that if NP equals P, then this language does get into P. And how can we do that? Because it's not obviously in either of these. Well, still it's going to work out. So in order to see that, let's define another language I'll call equivalent circuit, which is kind of the problem that the verifier kind of wished it could do in our hypothetical thoughts about whether this language is in co-NP. So let's define this to be the language of all pairs of circuits, C and C prime, that just compute the same function. So they're equivalent. The truth table of C is the same as the truth table of C prime. My C's, my parentheses, and my T strokes all look the same. So hopefully you can read that. OK, so yeah, cast your mind to this language for a minute. You're given two circuits. You want to decide, do they compute the same function? So this is in a complexity class that appears on the board already. Can somebody tell me which one? Right, this is in co-NP. I hope you can see that. Right, to show that it's in co-NP, you can show that its complement, non-equivalent circuits, is in NP. So if you're given two circuits and you want to check that they're non-equivalent, how could a prover give you a certificate that would convince you of that? Well, the certificate would just be some string where they differ. Okay, so the prover gives you the string, and in polynomial time you can plug it into C and C prime and check that they give different outcomes. Okay. Okay, so you can certify when an input is not in this language efficiently. Okay, good. So, right. So now check this out. If okay, NP equals P, well, then the complement of this language, non-equivalent circuit, is in NP. Well, that's definitely true. We don't need this supposition for that. But if NP equals P, then this equals P. Okay, so under the assumption NP equals P, non-equivalent circuits, this language can be checked in polynomial time. And kind of now you're in business for this earlier idea of putting the minimum circuit problem into co-NP. Okay, so just to state it, let's say, and now, still assuming NP equals P, just the complement of the language I started talking about, minimum circuit. So non-minimum circuits is in, NP. Okay, because why is this? Well, I'll describe it to you, let's say, using the language of non-deterministic Turing machines instead of verification, just for fun. So given circuit C, okay, where you're trying to check if it's in this language, so you're trying to check if there's a smaller circuit that does the same job. How can you check that? Well, a non-deterministic polytime machine can just guess a smaller circuit, C prime, smaller meaning having fewer gates, a smaller inequivalent. Okay, and then deterministically, and this is the trick, deterministically verify that using, let me call this fact star, the fact that the non-equivalent circuit problem is now in P. Okay, so under the assumption that you can efficiently check if two circuits are non-equivalent, the non-minimum circuit problem is in NP. Okay, and then finally, well, this is P, so non-min circuit is in NP, and P is close under complement, so is min circuit. Okay, so as I said, even though we have this language, it's seemingly even bigger than, it's harder than NP or co-NP. It too falls to be in polynomial time, just under the assumption P equals NP. Any questions about that explanation? Okay, so now we can ask ourselves, how did that happen? Let me give kind of another proof of the same fact, or to sort of an alternate viewpoint on what we just saw. And it'll help us define the polynomial time hierarchy, which is, as I said, kind of the set of languages that fall to being in polynomial time as soon as P equals NP. So another way you could look at what just happened is a circuit C is in the language of min circuit if and only if. Okay, let's try to think about it in terms of quantifiers, like for all and exists, which is like a good way of understanding NP and co-NP. NP has this kind of exists flavor. Co-NP has this kind of not a for all flavor. So I'm going to be very slightly informal here, but let's say that a circuit is in the language of min circuit if and only if. For all other circuits, C prime, whose size is smaller than that of C, there exists a string X such that C prime of X differs from C of X. Okay, so I hope you agree to this. C is in the min circuit language if all circuits C prime, which are smaller than C, have the property that there's a string on which they differ from C. Okay, and now I'll use some propositional logic. I'm going to replace like A implies B with not A or B. Okay, and now, there exists quantifier is really like a gigantic OR, right? You're like ORing over all possible x's here. And then we just are ORing something else. So like OR is associative. So we can actually move this there exists like over here. Even though this doesn't reference x, it's okay. So this is the same as for all C prime, there exists an x such that either size of C is not less than, C prime is not less than size C, or C prime x does not equal C of x. Okay, I could have just written this initially and then just said like, think about it, like this is equivalent to it. It's a little bit weird because like you kind of quantify over x before you talk about this, but anyway. And now let me just observe that this piece is polytime checkable. Okay, so there's some quantifications here. But this piece, if I give you two circuits, C prime and C, and also a string X, it's easy for you to check that, like, do this computation to see what's the deal with their sizes, and also do this computation to see what their values on X are. OK, so we have a kind of a characterization of the language min circuit, which is of the form some quantifiers for all C prime, there exists X, and then some polynomial time checkable condition. And really, I was slightly uncareful here. Like, what does it mean, quantifying over circuits? It's really quantifying over the string representation of those circuits. And I should also, it would be nicer if I had like only quantified over strings that are of length polynomial related to C. But I didn't want to like junk up this statement with a lot of commentary about encodings and stuff. So this, I think, gets across the idea. But actually, while I'm here, let me introduce a tiny bit of notation, which I think I'll only use once in this class, but we might use it later in the course. So let me just, as a brief side note, introduce some notation. If you have a string X in mind, I'm going to use this notation. Exists superscript P of Y means there exists a string Y with the length of Y being at most P of the length of X, where P is a polynomial. OK, so in the theory of computation, like you're always quantifying over strings, and you're almost always quantifying over strings that have a length, at most polynomial in the previous strings you've talked about. So it's a little notation for that. OK, so this way of understanding the min circuit problem in terms of like some quantifiers and then some polynomial time computation is actually a great way to classify difficult problems and stratify them into complexity classes. And that's what I'm going to do just now. So actually, right now I'm going to define an operator on complexity classes that takes a complexity class and makes a new complexity class out of it. And in that way, we'll get lots of complexity classes, which is, of course, desirable. So let C be a complexity class. Really, that's just a collection of languages. So we're going to define some new complexity classes. OK, and the first new complexity class is going to be called exists C. OK, that's the name of the new complexity class. And which languages are in exists C? It's those where, well, L is in this class, exists C, which I'm defining, if there exists a language R in the base class C, such that X is in L, if and only if there exists a polynomially bounded Y such that the pair XY is in C. Okay, so somehow it's extending C by existential quantification. Like, roughly speaking, you're in this language exists C. X is a language is in here if it can be characterized as something's in the language if there exists a string Y such that some C checkable relation involving X and Y. Yes?
So do you use some polynomials that we're like taking more over on that side of this, or?
Yeah, this actually notation is not like 100% perfect. It's like L is in this if there exists an R and a polynomial P, such that you have the characterization X is in L if and only if exists there a P bounded Y such that this. Yes?
What does R have to do with the bottom line? How does?
Great. This should say R. Thank you. Does that make more sense? Great. And let me define another such complexity class for all C. So a language is in this complexity class for all C if still there exists here. If there exists an R in C such that L has the following characterization. X is in L if and only if for all polynomially bounded y, x, y is in R. Okay, let's do some examples. Exists P. This is the same as another well-known complexity class. Which one? NP, I hope you said. Yeah, this is just another name for NP. Okay, that's sort of like the verifier definition of NP, right? You're in NP. If there's some kind of, this is like the verifier, the language of things that the verifier accepts, such that X is an L if and only if there's some polynomially bounded certificate Y, which the verifier accepts. And how about for all P? It's con P, yeah. Great. How about this one? There exists, what complexity class am I going to apply it to? I'm going to apply it to the class called there exists P, aka NP. So what is exist of that NP? Yeah, it's still NP. And why? Well, see, this doesn't really change if like, this is like X is in the language if there exists a Y such that there exists a Z such that X, Y, Z is in R. And, you know, polynomials are closed under addition, so just existentially quantifying over a Y and Z is just the same as existentially quantifying over like a bigger string. Okay, and so for all P is the same as for all P, which is common P. Okay, but now it's time to get something interesting. What about this class? For all there exists P. This is like, you know, language is in this class if it has a characterization, well, of this form, right? Like, for all something, there exists something such that polynomial time checkable something. Okay, so, well, it is what it is, but as we see from the left pane, whatever it is, this min circuit language is in it. Great. Okay, so it seems like a cool class. I mean, it seems reasonable. Like once you've thought about NP and co-NP, and you've made this observation, it seems like a logical class to define, I suppose. It actually has a name. It's called Pi2P. So here's infinitely more complexity classes for you. Only countably many, though. This complexity class, sigma IP, is defined to be, well, like there exists for all, there exists for all, there exists, dot, 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 P, where there's I quantifiers here, and it starts with for exists. Okay, this sigma somehow is tells you that it starts with for there exists, and the I is the number of quantifiers. So what it ends with depends on whether I is even or odd. Okay, so for example, sigma 1p is just yet a third name for NP. And its friend is pi IP. And that's the same thing, but starting with for all. Okay, so for example, pi 1p is another name for co-NP. Indeed, in general, this is just the co of this and vice versa by De Morgan. Okay, so that's a lot of complexity classes. Any questions? Yeah.
Can we keep going if I is like some ordinal bigger than?
Ordinal.
Like I equal omega or omega plus 1.
Yeah. I don't really want to entertain that question, but in some sense we can keep going. We'll talk about that later in the class. There is a sense in which you can ask about, like, what if I is not a constant, but somehow depends on the input length x of x. Yeah, ordals, I don't know. Yeah. Anyway, okay. So let me return to the story that motivated the beginning of this, which was what happens if p equals np. And well, if p equals np, then all these classes become much simpler. So if p equals np, well, then here are some things that happen. Okay, then this class exists p. That's just np equals p. That's for sure. And as we saw by taking the co of this, for all p also equals p. This is just co-np. But now let's look at the next interesting one, sigma 2p, which is there exists for all p. Well, basically, this is like, sort of up on the board. A language is in here if it has a characterization like this, where x is in the language, if there exists a string y such that some for all p relation is true about x and y. But every for all p relation is now, by hypothesis, also a p relation. So therefore, anything that's in exists for all p is also in exists p. Let me call this little guy star. This is by star. Okay, but actually this is p. By this. P is, of course, contained in here, so sigma 2p also became p.
Can you explain why you put a subset but not equality?
Well, it's also equality. I just, it is.
Like by our definition, there exists for all p means there exists applied to a language for all p, right?
Well, this is a collection of languages. And I'm saying this collection of languages is a subset of this collection of languages. Now, it's syntactically clear from the definitions that, like, well, maybe it's not so clear, but it's pretty easy to see that this is also a subset of this.
No, what I mean is that in our definition there exists for all and language, let's say.
No, you can't apply it to a language.
Sorry,
Yeah.
complexity class Q, let's say.
Yeah.
So there exists for all Q. Define it as there exists applied for a complexity class for all Q.
Yeah, good. So this means exists applied to the complexity class called for all q.
Okay. And then if Q is equal to P, and we know that for all P is equal to P, then it can just plug in and just equal to there exists P. Just by definition, right?
Basically, yes. I mean, you're saying that,
I'm saying that
you're saying that if
class A equal B, then exists A equal exists B.
yes.
Right?
That is clear from the definitions. Yeah. Okay, good. Okay, and similarly, pi 2p, which is for all exists p. As Alex is saying, we now know that this is p. So this is for all p, which we also know is p. Okay, and this min circuit problem was we sort of still by the left pane is kind of visibly in this class, and this reflects what we talked about at the beginning, that if p happens to equal np, then the min circuit problem becomes np. Okay, and etc. So I mean, they all, like sigma 3p, pi 3p, they all become equal to p. For every I, sigma ip becomes equal to p. Let me draw a little picture of these many complexity classes we just invented. I'm sure I'll never find it again, having put it there. Okay, so B, this line means it's contained in. Okay, I'm going to draw it left to right. So P is contained in NP, it's contained in co-NP. Okay, this is also known as sigma 1. And this is contained in sigma 2p. This is contained in pi 2p. And we also have this. So maybe it's not immediately obvious, but like, I mean, if you have something like there exists for all, etc., you can drop out any one in the middle anywhere, and like you'll get a smaller complexity class, because it's like you just chose not to quantify over those variables at all. So like for this is like exists for all p. If we drop sort of this ability to quantify over here, we get there exists p, so that's why this is true. And conversely, had we dropped this one, we would get co-NP. So that's why this containment is true. Okay, so we can sigma 3p, pi 3p, etc. And all of these language complexity classes are called pH in the sense that this. pH is yet another complexity class. pH stands for the polynomial time hierarchy. And it's the union over I of sigma I. Okay? I could have also written the union over I of pi I because, I mean, sigma I is contained in pi I plus 1 and vice versa. In other words, a language is in the polynomial time hierarchy if it's in one of these sigma pi classes for some I. Okay, and the observations I've written here can be called the theorem that if p equals np, then the polynomial hierarchy equals p. Let me rephrase that. It's the same thing. Let me phrase it like this. If np equals p, then in fact the whole polynomial time hierarchy equals p. And let me make one more tiny observation. I guess, I don't know if you can see this. The polynomial time hierarchy, you might always want to have like an upper bound on what it is, just so we know where it's living. And a good upper bound is p space. Because if I give you like a relationship like a problem that looks kind of like this, or maybe even there's like 5 more alternating quantifiers back here, it's not hard to see that it's still in p space. You know, because even for this one, right, you just like enumerate over all c primes, enumerate over all x's. That's a polynomial amount of space. And you know, check this in polynomial time. You know, you can sort of reuse space when you're enumerating here. You got to be a little careful, right? Like for a fixed c prime, you're kind of, as you're enumerating over x's, you're trying to see if any x makes you happy here. But then as you're enumerating over c primes, you're trying to check that like every time you were made happy by some x here. Okay, so there's a tiny bit for you to keep track of, but it's not very hard to see that anything that looks like this, even with more quantifiers, is in p space. Okay, so as I said, this polynomial hierarchy is like some collection of like complexity classes of increasing power rising up from p, but staying below p space. Okay, any questions? So, okay. I said that if np equals p, then the whole polynomial time hierarchy collapses down to p. Of course, we don't really believe that np equals p. But a more believable thing, albeit still unbelievable, is that np equals co-np. Let me ask this question. What if np equals co-np? Right. So that's more believable because, I mean, it's possible that np equals co-np, but still they're both different from p. But if p equals np, then this certainly follows. Right, that's, in other words, in our glorious new notation, that's the same as saying this. So they might not equal p, but what happens? Well, for example, you know, sigma 2 p. Sometimes I stop writing the p, so I might just write sigma 2 instead of sigma 2p. All right, by definition, this is there exists for all p. As was pointed out, this is co-np, and now it's the same as np, so that this exists. There exists p. I'll write it like this. That's np. But as we saw before, exists p is the same thing as p. Whoa, what? Oh, yeah, sorry. Still living in this fantasy world of np equals p. Okay, and for example, pi 2p, let's see what happens here. This is, by definition, for all exists p. This is np, so by assumption it's co-np. That's for all p, which is for all p. Which, by the way, these things are equal. So you see these two classes, sigma 2p and pi 2p, also kind of collapsed down to np and co-np. And I won't bore you with it. I mean, sigma 3p, well, there exists pi 2p by definition. Pi 2p now we know is equal to exist p, so it's exist p, it exists p. Okay, so it also becomes equal to np and co-np. And you can kind of basically clearly see that everything in the polynomial time hierarchy will become equal to np and co-np. Okay, and this is a phrase that you'll see used for this is that the polynomial time hierarchy collapses to the first level. The first, referring to this 1 here. Okay, we assume that np equals sigma 1 equals pi 1. Okay. Let me give you another little quick illustration of this, just to goof around. Suppose we wake up one day and somebody shows that I don't know, pi 7p is contained in sigma 3p. That'd be kind of crazy. What happens then? Well, then pi 3p is certainly a subset of pi 7p. By the principle that you can drop some quantifiers and it doesn't make the class any bigger. Okay, so then pi 3p is contained in sigma 3p. So in fact, we get that pi 3p equals sigma 3p. Okay, but then of course, pi 4p, which is for all sigma 3p, equals for all pi 3p. Okay, and this is for all exists for all p. So you can merge these two for alls, and this becomes pi 3p. Okay, so sigma 4, pi 4 collapsed down to this. You can also show that sigma 4p equals, it collapses down to this, pi 3p equals sigma 3p, and etc. The whole polynomial time hierarchy will equal pi 3p and sigma 3p. Okay, and that's called pH collapses to the third level. Okay, so once you basically get a relationship between some of these complexity classes, which is not implied by the diagram, where let's say 2 are surprisingly equal, then the whole polynomial time hierarchy will collapse down to that. Yes?
Can you explain why sigma 3p is contained in pi 3p?
Sigma 3p is contained in pi 3p. Oh yeah. Let's see. As I was writing that, I was like, why?
You can do it sigma 4p.
Maybe I didn't get it right. Let's see. So we got pi. Okay, so let's see. Okay, let's see. So we definitely have this one, right?
Can you take not?
Yeah. Well, wait a minute, no.
Can you just take not of each side, and then pi 3 becomes sigma 3?
Yeah, that sounds pretty good. Let's see. So let's try to expand upon that. Yeah, this is an example of if we have co-np, a simpler version. We want to show that this implies that they're in fact equal. Right. So if you have a language so let's say you have, let's just do it in this case, it's a bit easier. Let's say if you have, okay, so we need to show that np is a subset of co-np. I'm assuming this. So let L be in np. Okay, then L bar is in co-np, which is in np by assumption. So now we have L bar is in np. So therefore, L is in co-NP. So we show that NP is a subset of co-NP. Good. That was a little argument I skipped. Yeah. Great. OK. So the popular hypothesis is that the polynomial time hierarchy does not collapse to any level. But basically, all of these classes we introduced today are all distinct. This is a popular hypothesis in complexity theory, which is that pH does not collapse. At all. This is stronger than P does not equal NP. Right, this implies that P does not equal NP. Because if P equals NP, if you have a surprising equality here, then the whole thing collapses. But still people consider it believable. It's very popular in complexity theory. Now, why do people believe this? I don't know. I mean, if you don't see any good reason why two classes should be equal, then I guess it's natural to believe that they're equal. I mean, it's like with the min circuit problem, which is in pi 2 p. Couldn't really see any way in which it would be in, it's pi 2 complete, I guess, by the way. Couldn't really see any reason why it would be in NP or co-NP. Like, that seemed very implausible. So yeah, conjecture that they're equal. It's not equal. By the way, it's not like, there are kind of like natural problems in these complexity classes, and even some natural problems in like sigma 3 and pi 3. Above that, it's kind of getting very unlikely. So I can't say that like people have like so much intuition for them, but like, if you believe they're all different up to here, like why would you believe that they suddenly become equal? Yep.
I don't know, like P equals NP is a stronger statement than that pH collapses to something, but isn't it in a sense, wouldn't it be like even weirder if it collapsed to like level 7 than if P just equaled NP?
I think so. Well, yeah, arguably. I mean, that would be very bizarre, right? Like if it's going to collapse to something other than P, what is it going to collapse to? That would be weird. Yeah?
Is it believable that it collapses to the first level? Is that
I mean, I don't believe any of these things, so it's hard to say. But I mean, maybe because like 1 is the least unnatural number, like it's more natural than 7.
Would that be more believable than, say, level 7?
Formally, no, right? But like somehow intuitively, yes. I mean, yeah. Yeah. OK, so it's popular to assume this. OK, I mentioned just 2 seconds ago in passing the notion of complete problems. And it's very good in life and complexity to have a complete problem for a complexity class. I mean, you shouldn't really care about a class if, well, a good reason to care about a class is because it has a problem in it that you care about, and that problem doesn't seem to be any smaller class, okay? Which is kind of basically the definition of a complete problem for a complexity class. So the min circuit problem we mentioned, I guess it is complete, I think, for pi 2p. I say that, I think it's true. Maybe I'll have to double check my sources. But I do know for sure one complete language for each of these complexity classes. So let's say, does sigma IP have a complete language? And the answer will not surprise you. Yes. And one example is the language called sigma isat, which it's going to look kind of tautological, but it's all the true quantified Boolean formulas of the form. Well, you might not be surprised. There exist, and then some variables for all, and then some variables, etc. And then some Boolean formula of the variables, some propositional logic formula of the variables. Okay, where there's like I blocks here. And this thing is just has like some ands, ors, and nots applied to these variables. Each of these xj's is like a block of Boolean variables. Okay, so like if I is 1, this is like saying sigma 1 sat is complete for NP. And sigma 1 sat is just like the true statements of the form. There exists some x's such that some Boolean formula of those x's, which is like saying the Boolean formula of those x's is satisfiable. Like this is just a different way to write the SAT problem, sigma 1 SAT. Okay, so it's kind of visibly clear that these languages are in, like sigma I SAT is in sigma IP. Why is it complete? So like it's kind of, I think, clear that SAT is in sigma IP. Why is it complete? Well, that's an exercise for you. But it's basically Cook-Levin. I mean, basically, it's like saying, oh, it's no longer on this board. But if you remember what used to be on this board, you know, you're in sigma 2p if, like, as a language, if there's like a characterization of you of the form, there exists some string such that for all other strings, and then some polynomial time computable predicate of the strings. Okay, and then you just kind of Cook-Levin to convert that polynomial time computable predicate into a Boolean formula, or a circuit if you like. I don't care if you change this to a circuit that does the same thing as the polynomial time computation. Okay, so it's just Cook-Levin again. Great. While we're collecting up sort of unsurprising observations, let me make this unsurprising observation, which I again leave to you. Obviously, pi I and pi I SAT, where you start with a for all. Sigma IP is closed under polynomial time reductions. And I never mentioned it in this class, but whenever I say reduction, polynomial time reduction, I only mean many one reductions, like not the Cook-Turing reductions. We don't like those. Just the reductions where you take one string, output another string, such the input string presence in A is equivalent to the output string's presence in B. Okay, in other words, what I'm saying here is if, like, i.e., if A many one reduces to B, and B is in sigma IP, then A is in sigma IP. Okay, this is like a famous fact. When I is 1, you know, if A reduces to B and B is in NP, then A is in NP. Okay, and that relies certainly on this being many one reductions and not Cook reductions or whatever they're called, Turing reductions. Good. Okay, so now let me ask a variant of this question. Does this class, polynomial time hierarchy, have a complete language? All right, this is the definition of the polynomial time hierarchy. And the answer to this question is basically no. Well, what is this asterisk? Unless this popular hypothesis fails. Let's say assuming this popular hypothesis. So let me elaborate on that. Suppose that there were a language which is complete for pH. Okay, well, what does that mean when a language is complete for a complexity class? Also, in this course, if I don't specify otherwise, complete, or in fact hard, means with respect to many one polynomial time reductions. Well, it means two things, right? Like an NP complete, it means that L is in the thing, so L is in polynomial time hierarchy, and everything in polynomial time hierarchy reduces it to it. So for all A that are in the polynomial time hierarchy, A reduces to L. But now let's look at the conjunction of these two things. If L is in the polynomial time hierarchy, then by definition of, you know, a set being in a union, it's in one of these for like some particular I. Okay, so this implies that there exists some like specific J such that L is in, let's say, sigma JP. Okay, I can put sigma here because if it were in pi j, then I just increase j plus by 1 and get it. Oh, I guess I just took the union over sigma here. Okay, but now, I suppose appealing to this fact, if you have a language A and it reduces to L, and L is in sigma JP, then this implies that A is also in sigma JP. So the conjunction of these two facts shows that for every language in the polynomial time hierarchy, it's also in sigma JP. In other words, this means that in this phraseology, pH collapses to level J. Okay, so there can't really be one language which is like complete for pH because it would have to be in pH and it would have to sit at some level. But if that language was also like the hardest language for pH, then everything would be in pH would be in that level, which is considered unbelievable. Okay, questions? So pH is a bit of a funny class. I mean, it's not so much a class in so it's in and of itself is just like a shorthand for the collection of all the fixed levels. Yep.
The fact that sigma IP is closed under polynomial time reductions.
Yeah.
Does that imply that the fact that it includes P, or are there classes that include P that don't have that state?
Basically once a class kind of has the power, it's not a well-defined thing, but once it has the power to do like deterministic polynomial computation, then it's usually closed under many one polynomial time reductions. It's a more exciting statement than I thought. Yeah, do you have a question? Okay. All right, let us return to a little bit to Bill's question about the ordinals. Yeah?
Exist pH, is that just pH?
Yeah, that's right. Because, I mean, that's a fun question. I'll put that on the quiz. There exists pH equals pH because, a language is in here if L is in here, if like it has a characterization like X is in L, if and only if there exists Y such that XY is in R, where R is in pH. But if R is in pH, then by definition, it has to be in sigma, yeah, that's true, sigma J for some J. So in fact, this L is also in exists sigma J. So it's in sigma J, so it's in pH. Great. Right, so notice that like for every fixed I, we defined sigma IP and we defined sigma I sat, and sigma I sat is complete for sigma IP. Now notice for sigma I sat, I defined it as like you have I blocks of quantifications where I is fixed in advance, but I could consider not fixing I in advance and just I consider the problem of you're given like any true, the language of all true quantified Boolean formulas. So what about this language? TQBF. It looks like just all strings that are of the form can start with anything, doesn't matter. Okay, so you can quantify over variables, and you quantify over maybe however many you want. Maybe you write down a formula with like n bits in it, and like square root n of those bits are devoted to having, I don't know, n to the 1/3 quantifiers over n to the 1/6 variables, and then this is a bunch more stuff. I mean, where, yeah, the number of quantifiers is maybe not constant, but related to the size of the input. Well, that's a language. And as maybe I hope you know, perhaps if you took undergrad complexity last year, this language is p-space complete. Okay, so this is a complete problem for this big class that contains the polynomial time hierarchy. Okay, so if you didn't know that fact, well, now you know that fact. Any questions? Yeah?
So that means if p space equal pH, then pH would collapse to something, and that would be really weird. So we think p space doesn't equal pH.
That's a good question. That's right. So if pH equals p space, this really might have been on, well, anyway, a quiz. P space equals pH, and there's several things you can see. For example, if p space equals pH, then pH does have a complete language because p space has a complete language. And then we'd see the hierarchy would collapse. So it's actually kind of crazy if you think about it. The assumption that pH is big implies that it's small. Okay? If you assume that pH somehow extends up big enough, that includes p space, and the observation is that like, oh, then the hierarchy collapses and it actually all comes down to some finite level. That's cute. Yep.
So TQBF is the union of all sigma I sats, right? Is that?
Nope. No, so like the union of all these languages is not TQBF.
Is that because like every sigma?
Well, wait a minute. Hold on. Maybe I got that wrong. No, I'm wrong. It is. The union of these guys is TQBF.
Like there's no funny stuff with like the I being constant versus a function of the input. Right? That doesn't matter, right?
No. So like for any string that looks like, you know, a sentence in first order logic, if I write down a string for you, then there is some I, namely the number of sort of quantifier alternations, such that, you know, that string is in, assuming it's true, to sigma I sat and no lower one. It's true.
Are we talking about sets of languages?
Yes.
So in any language, you might not have like a fixed I.
In the language TQBF, there is no fixed I. But Arora does make a good point that, in contrast to the fact that the union of these complexity classes is pH, which we believe is smaller than p space. On the other hand, the union of these languages is TQBF, which is complete for p space. I never really thought about that, but I think it's true. Whoa. Any other questions or comments? Yeah?
So does this analysis of like there exists world, does it work for language other than, like for complexity classes other than P, like is it useful to study exponential hierarchy, or is it the same thing? Or P space hierarchy? Or is that the same, or that just collapses?
That collapses immediately. Yeah, it's just p space.
Yeah, but it's useful to study it for small space classes, like L. But it takes a little bit of thinking to define it, maybe. But that leads me into the next part of what I'm going to say. So there are actually several alternative definitions of the polynomial time hierarchy. This was not the original definition, actually. It was defined, actually, Karp in his famous 72 paper where he like has those 21 NP-complete languages, he has like one throwaway line where he obliquely suggests that he was thinking about the polynomial time hierarchy. That is defined by Meyer and Stockmeyer in the early 70s, and Stockmeyer had a different, I guess, paper about it. So it dates back to those olden days. But here's another way that was not invented until, it was like the third definition of the polynomial time hierarchy, but I'm presenting it second. So mentally switching gears a little bit here to talk about a new concept called alternation, which is related to non-determinism. Okay? So recall what's up with non-deterministic Turing machines. Okay, so a non-deterministic Turing machine, people sometimes like to draw it as having a computation tree on a given input, let's say. So if you have like a non-deterministic Turing machine and a fixed input, then people kind of like to draw a tree for it, where like the circles are kind of the configurations, which means, you know, state plus tape contents. And you know, in a non-deterministic Turing machine, like every time step, it can use one of two transition functions, or it non-deterministically uses one of two transition functions, or it has two possible outgoing configurations. So you can just draw them as like a tree. Okay, so this would be the initial configuration. And these outgoing edges refer to the fact that this is sometimes called non-deterministic branching. And sometimes as you're going along, you get to a configuration, and then the Turing machine decides to reject. But that doesn't mean sort of the whole computation is said to reject. All these branches, continue out. Some of them accept, some of them reject. Eventually, they all accept or reject. But then, the definition of non-determinism or non-deterministic time (NP) is that kind of you say that the computation is sort of said to like overall accept if and only if at least one leaf sort of locally accepts. Okay, that's one way to think about non-deterministic computation. It's always branching. Eventually it accepts or rejects, but you judge the whole computation to have accepted or rejected based on whether there's at least one leaf that accepted. Okay. So NP is the class of all languages accepted by such a machine in polynomial time, where the depth is polynomial and the length of the input. And we sometimes will talk about a co-non-deterministic machine. And it's the same model of computation where at every step there's two possible transitions and you kind of fictionally imagine all possible transitions, but you just judge whether the overall computation is accepted differently. So it's the same, except, but you just say that overall accept means that all leaves locally accepted. Right, so unsat is in NP, or co-NP. So it's solved by a polynomial time co-non-deterministic machine. What does that mean? You imagine the machine that uses its computational branching to try all possible assignments. And at the end, if it falsifies the assignments, falsifies the formula, you locally accept. And then the overall computation is said to accept if all the local branches eventually accepted, meaning all the assignments falsified the formula. Okay. So when you look at it this way, right, there's sort of a natural thing to do. Non-determinism, or this way of judging the overall acceptance is kind of put an OR gate in all the branches points. Right? If you say that accept is true and reject is false, then if you just write OR on all the internal nodes, then the roots kind of tells you whether you're supposed to overall accept or not. Okay, and co-non-determinism is you put an AND everywhere. And that's how you define whether this kind of branching computation is said to overall accept or reject. So now this definition is a little crazy, but it's entertaining to get used to it. An alternating Turing machine is well, it's like a non-deterministic Turing machine, but it gets to decide every node whether it wants it to be an OR or an AND. Okay? Okay, so it looks like a non-deterministic. Okay, it looks like a Turing machine with the states and the tape and everything. But first of all, it looks like a non-deterministic one in the sense that it has two transition functions. So at every configuration, there's two possible ways it can go. But it additionally has some little thing built into the definition that for every configuration, it specifies whether these two transitions are to be judged in like an AND way or an OR way. Okay, and then like whether or not the overall alternating Turing machine is said to accept or reject is like, well, you find out what happens to the leaves and like filter it up through this formula of ANDs and ORs. And there's some terminology you will hear describing it. These ones where like you do like an OR branch, it's called existential guessing. And this kind is called universal guessing. Okay. So it takes a little thought to get your mind used to it, but let me like say some words that once you're used to it, you'll come to say yourself. Here's an alternating Turing machine. Polynomial time, I should add, but polynomial time Turing machine that decides the min circuit problem. Okay, so I will not describe it in the language of Turing machines, like, you know, it's a 7-tuple or whatever, but I'll describe the algorithm in English. So on input C, remember you're trying to decide, is it true that all smaller circuits than C compute a different Boolean function? So you universally guess smaller, you know, a C prime of smaller size. And what does that really mean? It means that the Turing machine like maybe writes a bunch of bits onto its tape describing a circuit, C prime. And as it's doing them, it writes all these bits non-deterministically. So like the tree branching kind of gets to a situation where all the leaves so far correspond to all possible strings of a certain length that are supposed to represent C primes. And as it's doing that, it's always like doing this one. It's always like kind of anding over the possibilities. So it's sort of, therefore, like anding over all possible C primes. And then a complexity theorist would say, then it existentially guesses, you know, an X, appropriate size. So in other words, it uses more non-determinism to write down more bits. And as it's doing that, so it writes down all strings X as you go across the branches. It's like ORing. So in some sense, it's building a tree with like lots of ands in it. And like here you have all the different possible C primes. And then it like builds a bunch of more trees off each one that all have like ORs in them everywhere. And here there's all the different X's that you might have. So like finally each configuration down here has got one C prime and one X written down. And now it either, well, it accepts if and only if they are C of X, this is the input C, differs from C prime of X. Okay, so that's how you would describe this alternating Turing machine in words. And then you see it does the right thing, right? Like it accepts C if and only if for all smaller circuits C prime, there exists a string where C and C prime differ. Okay, that's how ANDs and ORs work. Okay. So alternating Turing machines are, you know, useful as ways to describe algorithms that kind of have this existent for all sort of behavior built into them. How do we relate this back to the polynomial time hierarchy? Well, okay, so an alternating Turing machine is said to be of a certain type. And let me just say, define type sigma 3, for example, and then you'll get the gist. For example, if on every computation branch in its computation tree, the guesses or the style of the branch point being OR or AND look like or for a while, and then and for a while, and then or for a while. Okay, so a sequence of ors, like a sequence of existential kind of guessing, then some universal guessing, then some existential guessing. Does that make sense? Good. I should mention that like if the machine like wants to like just like relax for a bit and do some deterministic computation, you can just like imagine that it's in the model. Like if you like, these branches can have some like only one output that just works deterministically. Or formally, you don't need to do that. You can just say that like, oh, it has to do a guess at every step. But like, it can like not change the type it's in by like, oh, if it's lately been doing some OR guesses, then it can like just, if it wants to act deterministically, it can like use existential guesses here and just ignore what it guessed and continue. Yeah?
So the number of ORs guesses varies by input too, right?
That's right. So it's of type sigma 3. Yeah, let me add this. If for all inputs. It's risky to write for all here because it's sort of what we're talking about. For all inputs and on every computation branch, it has this property. Yeah. Good. Okay, so like this alternating Turing machine, if you look at it, this one is of type pi2. Okay, because at first it does a bunch of ands, then it does a bunch of ors, and then it's deterministic. Okay, so the number of alternations is what sort of it pays for. That's the thing you care about here. Okay, so here's, to relate things back to what we saw before, this is a little exercise for you. I think it's hopefully clear. Actually, I guess it takes some thought, but let me say this is an exercise for you. Sigma IP, the complexity class that we've talked about, is equal to the set of all languages decidable by a sigma I type polytime Turing machine. ATM, alternating Turing machine. Yeah, because really both of them, like if you remember the original definition, like sigma 3p is like you're in there if you have a characterization of the form exists y such that for all z such that there exists w such that some polynomial time checkable predicate of the real input x and the other blocks of strings y, z, w. And they should be polynomially, the length of those strings should be polynomially related to x. It basically matches and type checks. So it's sort of like just a different way to describe sigma IP and pi IP. In fact, one reason that, in some sense, the only reason I brought it up, this alternating Turing machine description, is it allows you to like talk about alternation in a way that's like a little bit more refined than just saying, oh, this is sigma IP, this is pi IP. You can sort of apply it to models other than P. So in particular, you can define sigma I time to be a complexity class, sigma I time, like T of n, to be, again, like all languages L decided in order T of n time by sigma I type alternating Turing machine. And so you see the time bound you get, like if you put in, I don't know, 2 to the square root n, or if you put in, I don't know, n to the 1.1, like some fixed thing, it kind of sort of simultaneously bounds like how many different guesses the Turing machine can do and also how much time it can run in a way that wasn't so easy to say when we just defined sigma IP initially. Okay? You can also define sigma I space, and that can be interesting. Good. So we're a little bit early, but perhaps this is I won't say too much more. Just because we'll need it in like 1 or 2 lectures, I will just tell you, and you can think about why it's true, that there's a time hierarchy theorem for these classes. Okay, so if little t of n plus 1 is little o of big T of n, okay, and like they're appropriately constructible, I didn't even have the energy to look up which of little t or big T needs to be time constructible, so let's say both of them. Then, for all I strictly greater than 0, we have this time hierarchy type theorem. So sigma I time little t of n is contained in, but not equal to sigma I time capital T of n. Okay, so if I is 1, then this is the non-deterministic time hierarchy theorem. It's like saying that non-deterministic time little t of n is a strict subset of non-deterministic time capital T of n. It's exactly, this is the funny condition we had for that. And if you wanted to prove the same thing, but like for a sigma 2 time, it's really, I'll leave this an exercise. It's like basically identical to the proof of the non-deterministic time hierarchy theorem. Basically, that proof really didn't use that much about non-determinism. It used 2 things. First of all, it used the fact that like if you have a non-deterministic time t of n machine, you could simulate it deterministically using 2 to the that much time, 2 to the t time. That's a pretty weak statement, but that's also true about like sigma 3 time. I mean, you know, if you just like enumerate everything, you can always solve it deterministically given exponentially more time. That's basically it. I guess do we use like one slight thing that like very fast simulation of k-tape machines by 2-tape machines with like only constant slowdown in non-deterministic time. And as soon as you have at least some power of non-determinism, you can do that old trick. Yeah, so this is true. Now you might think this is like very abstruse, like okay, I defined alternating Turing machines, and then like not even like sigma IP, but sigma I time t, and then it's like let's do the time hierarchy theorem for it. But in 2 lectures, I'm going to prove some results of this I mentioned before, this flavor that like sat is not solvable even on like RAMs. In time, for example, this is the one that they do in the textbook, n to the 1.2 with space n to the 0.2. That's a theorem. It's if I only give you a small amount of space, like less than linear space, let's say n to the 0.2 space, then I actually can prove a super linear time lower bound for SAT. It's not amazing. We still think SAT should take exponential time, but it's better than like order n, which is the only pathetic things we can prove otherwise. So this kind of thing is a cool theorem. It was proved in, I don't know, mid to late 2000s. And as you'll see, like we're going to need the non-deterministic, we're going to need the time hierarchy theorem for like sigma 4 time to like prove this theorem. That's pretty cool, right? Okay, so this is why I mentioned these things. Okay, so next time we'll talk about a 3rd definition of the polynomial time hierarchy involving oracles, another glorious topic, and then we'll prove this theorem. Is that a question? Yeah. What is the question? The question is there a way to define p-space in terms of alternating Turing machines? Yes, p-space is the same as alternating polynomial time, where you're allowed any type. So that's pretty cool. Maybe you'll have to prove that at some point in your life. I don't know. Otherwise, you know the fact. Yeah. And alternating log space equals polynomial time. That's another cool fact.